6 undergoes fission, it can actually produce other products besides barium and krypton. So the products of the masses will usually have a ratio of 3:2. Now pause over here and try to figure out how many neutrons will be produced and what will the proton number be for strontium B. So when I see this kind of questions, the first thing I'll do is I'll realize that this is gamma radiation. Gamma radiation does not have any protons, does not have any neutrons, does not have any mass. So it'll be 0, 0. Then I'll write down the mass number and proton number for neutron, which is 1, 0. Okay. Then I'll tabulate the top values and the bottom values and see what is missing. So if I do the bottom first, 92 minus 54, minus 0, minus 0, you end up getting 38. What about for the top values? 236 minus 134 minus 90 minus 0. What do you get? You notice that you get 12. So you end up producing 12 neutrons. Pause here and try this out. Again, I'll start off with gamma. So gamma is 0, 0. Then neutron would be 1, 0. And then I just count the top numbers and the bottom numbers. Left hand side should be equal to right hand side. So you end up getting 13 neutrons and the proton number for plutonium will be 94. Again, pause here and try this out. You should have gotten this. Quite simple, right? Okay, let's move on to chain reaction. So just now we just talked about one reaction where one neutron collides with a uranium nucleus. So what's going to happen is that remember we said that no matter what, during fission, there'll be lots of neutrons that will be produced, right? Now, each of these neutrons that were produced can cause more uranium nuclei to split. And this avalanche effect is called the chain reaction. So you see, when it produced, this is the number of neutrons that were produced from the previous reaction. Each of these neutrons will end up colliding with more uranium nuclei. And then each of these, if they produce another few more neutrons, right? Can you see that the effect is just get bigger and bigger? So we call this a chain reaction. Now, nuclear fission reactors. So this is where the nuclear reactors will produce lots of energy from nuclear fission. And what it does is that the thermal energy that has been produced will convert your water into high pressure steam. Then this steam will drive turbines, which consists of your magnets, right? Sorry, turbines are just the fan, that's the fan-like thing, okay? Which will rotate your generators with your magnets to produce electricity. So we have learned this in the last topic on electromagnetism. Go to page 254 of your textbook. Please read through the entire process, okay? So this is how a simple diagram of a nuclear power plant will look like, which we have also gone through last year on the topic of energy. Now let's talk about nuclear fusion. This is so fusion is the joining of two atomic nuclei to form a larger one. And normally this occurs in the sun and the stars, where they burn and they produce energy is released, or in the hydrogen bomb. Okay, that's it. That's all you need to know for nuclear fusion. Now we move on to radioactivity. Okay, so there are two parts to this. Today we will be talking about background radiation and gamma, beta, and alpha emissions. Then the next lesson we'll be talking about the rest of these. Okay, so half-life and stuff. Okay, so first thing about radiation is that there's something called background radiation, and it's around us all the time. So like it or not, we are all exposed to radiation. I mean, even all of you know, right? Your handphones, you always talk about, radiation from your handphone. Yeah. There's also rocks and soil. This gives off radiation. Cosmic rays from exploding stars and from the nuclear reaction that occurs in stars. Okay, and living things. So your plants, which when they absorb radioactive materials from the soil, they then pass it up the food chain. Now, the higher up you go, the more exposed you are to cosmic radiation. Now, this is a general percentage of where the background radiation that we face comes from. So can we detect radioactivity? we can either use a radiation badge or we use a Geiger tube and counter. All right, or we just call it Geiger counter. Now, how does a radiation badge do? It contains a photographic film, and just like how your photography, the normal film, right? It changes when light is projected on it. Your radiation badge will also change color. It gets darker as more and more radiation gets onto it. So that's how you can tell how much radiation you are exposed to. Okay, so radioactive decay. Now, when isotopes are unstable, they decay. And when they decay, they give out radiation, and that causes ionization. Now, what's ionization? We'll talk about it later on. So this phenomenon is called radioactivity, and the radiation that's produced is called ionizing radiation. Now, this is a random process. You need to know that. It's very important. You cannot predict when something's going to decay. You cannot predict, you cannot tell how much radiation will be, how much decays will happen. All right, it's totally random. So Henry Becquerel discovered radioactivity in 1896. Okay, so what's ionization? Ionization occurs when an atom loses or gains one or more electrons. Okay, so when an atom loses electron, it becomes a positive ion. So if you look at this lithium atom over here, this is uncharged. It has got 3 electrons now. When it loses 1 electron, we call that lithium ion. Now, because it loses electrons are negative charges, right? So if I lose something that's negative, I become positive. And when an atom gains electron, so if it gains negative charges, it becomes negatively charged. So it becomes a negative ion. Okay, so what is this alpha, beta, and gamma radiation and its ionizing power? Now turn to page 247 of your textbook. You can see this green table at the top. Okay, so you need to be highlighting the green table, all right? So what is an alpha particle? So remember we mentioned this just now, alpha particle. It consists of 2 protons and 2 neutrons. Okay, it is strongly ionizing. What does strongly ionizing mean? It means that when it passes through air, chances of it causing your air molecules, maybe your oxygen molecules or whatever, your air particles, okay, to become charged is very high. Then there is this thing called beta particle. It's a high-speed electron. It is produced when a neutron has decayed into an electron and a proton. So it's a high-speed electron. It is moderately ionizing. Now notice that for alpha, there are 2 positive charges. For beta, there is 1 negative charge. So it's still ionizing, but it's not as ionizing as alpha because there are less charges to it. For gamma rays, they are high-frequency electromagnetic waves. You learned this end of last year, right? So they are produced when an unstable nucleus loses energy. They are weakly ionizing. Why? Because they have no charge. So even if they pass through other molecules and particles, it's very difficult for them to either gain or lose electrons, or to cause the other particle to lose or gain electrons. Okay, so they're weakly ionizing. So please highlight this in your textbook under ionizing effect. The first, second, third, fourth, fifth, the 5th row. Okay, so alpha particles have strong ionizing effect, beta particles have got weak ionizing effect, and gamma rays have got very weak ionizing effect. What about penetrating power? What do we mean by penetrating power? Means we're talking about its ability to go through substances. Okay, so for paper or a few cm of air, it will stop the alpha particle. Why? Because alpha particles are generally bigger, right? So they are easier to stop. So they're not as penetrating. For your beta particles can pass through a few cm of air and or paper. Now, when I put 1 cm of aluminium or 1 meter of air, it stops the beta from passing through. But for your gamma, they can still pass through. How do I stop gamma from penetrating, from passing through materials? I need several cm of lead or 1 meter of concrete to stop gamma rays. So go to your textbook. You can see under penetrating effect, for alpha particles, they are not very penetrating. Highlight that. Highlight stop by thick sheet of paper, by skin, by a few cm of air. For beta particles, highlight penetrating but stop by a few mm of aluminium or other metal. Gamma rays, highlight very penetrating. never completely stop, though lead and thick concrete will reduce the intensity. What about deflection by magnetic fields? So, alpha particle, what charge do they have? Positive charge, right? So if it's moving in, if this is your magnetic field, so let's recall what we have learned in, which topic is this? Topic 21, right? You have your positive particle moving in. What's going to happen? It's going to be deflected, right? Because if you use your Fleming's left-hand rule, positive particle is as if current is going to the right. So what's going to happen is that if you have your magnetic field, your B field is going into the paper or into the screen right now. So FBI, B being your second finger pointing into the paper, middle finger, which is your current, going to the right, you have a force produced upwards. So it's going to move upwards this way, right? Beta is negative. Since beta is moving to the right, current will be to the left. So the force produced will be downwards. Gamma, no charge. So will it be deflected by magnetic field? Probably not. Now, let me erase this. So I know that alpha and beta are going to be deflected, but are they deflected by the same amount? So no, because your alpha being heavier will get deflected, but because it's heavier, it doesn't get deflected by a lot, by much. Beta being very light, very small, will get deflected by a lot. Okay, notice that your deflection for alpha and beta must be in different directions. Okay, due to the opposite charges. Then alpha with its larger mass will deflect less than beta. Gamma ray is not deflected because it's not charged. What about electric field? So for electric field, now if I have electric field from, I have two electric plates, okay, positive plate and negative plate. Alpha particles being positive will be attracted to the negative plate. Beta being negative will be attracted to the positive plate. Gamma, since there's no charge, will not be deflected. Same thing, alpha and beta, because they have opposite charge, they'll be deflected in opposite directions. Alpha again being heavier will be deflected less than beta. Okay, so on page 247 of your textbook and in your notes, can you please write this down? Highlight it. You need to know all of these. Okay, so relative masses. Relative mass of alpha is high, beta low, gamma no mass. Alright? Now, for something to take note of is that your alpha particle is identical to the helium nucleus. Because your helium is 4, 2. 2 means 2 protons, right? 4 means protons plus neutrons. So if I have 2 protons means I have 2 neutrons, which is like the helium nucleus. Now notice it's the nucleus, not the helium atom, because helium has got electrons also. But your alpha particle doesn't have got any electrons, so it's just identical to the helium nucleus. Okay, now the uses for these three radiation. For alpha particle, it's useful for smoke detectors. For beta particles, it's useful to monitor thickness of thin sheet of material. For gamma, to monitor thickness of thicker materials, because it can pass through thicker materials, right? It's used for cancer treatment and to sterilize medical equipment. So we'll stop here for today. You can start doing your worksheet 25.1. Alright? See you.